So we're now on to the most difficult part of acids, bases and buffers, which is buffers. Okay, and again, I'm wearing my funky t-shirt, so please put in the comments what you think it says, and if you've got any other funny chemistry puns, please add. Okay, so here we have our buffers and how do they work. And we're going to go over 6-mark questions during this. Buffer solution as a system that minimises pH. Now, really important, minimises. Don't look up all those definitions on the thing that say it keeps it the same. Minimises, okay? Changes, pH changes on addition of small amounts of acid or a base. This is a really good thing to do in the lab, and when I do it in the lab, I physically kind of do it in front of everybody. It's a lot. I shouldn't really say this, but a little bit better than watching the video. But I've put as many pictures as I can in to try and make it as easy for you. So here we have our beakers. Now inside our beakers, we have got, we're going to make a buffer. So we're going to make a buffer in here. Okay, and what we do to make a buffer, to make this buffer solution that minimises the pH changes, that keeps the pH change roughly similar, okay, is we take a weak acid. So there's our weak acid. And then over here, we take a conjugate base. So the question is, how do you make that? How do you make the conjugate base, and what do we do with the weak acid? Okay, and that makes our buffer. Okay, so the first and easiest method to make a buffer is to take the conjugate base of the weak acid and add them together to make the buffer. Now, another way of doing it is taking excess weak acid and a strong base, such as sodium hydroxide, and that will also make a buffer. So we have got 2 ways of making buffers, okay, and we'll go through both of those ways and the calculations in the next video. Okay, but for now, we'll just explain how you do it. So there's the buffer going over to the side. You've got your definition, make sure you remember it. So we're going to talk about the first one, weak acid and a conjugate base. So ethanoic acid and its conjugate base. So what is its conjugate base? So its conjugate base is this thing here. And it's the base that's created from the acid. Now, if that's the case, creating a conjugate base is quite simple. You can add a metal to create a conjugate base. Okay, you can also add a carbonate to make a conjugate base. You can add a sodium hydroxide to make a conjugate base. There's many different ways, but the easiest way is just to add a metal. And you get the metal on the end there. And the other product is a gas. Because it's a gas, as long as you add these in the right amounts, you'll get pure sodium ethanoate. That's what this is called, sodium ethanoate. Okay, and then what you can do is just add it as your conjugate base. Now, sodium ethanoate is an ionic salt, okay, and it's fully ionized. So that basically means ionic there, which means it has a higher melting point than normal covalent compounds because it has an ionic bond in. Okay, so really, really important that as well. Okay, and it's fully ionized, which means the sodiums will separate onto the solution, leaving you behind your lovely conjugate base. Okay, and there you go. So if that is the case, that conjugate base will be in this container here. And then the weak acid will be in this container here, and you just go and you dump them in the same place. Now, if that is the case, okay, you will have this equation. So there's 2 things you have to do. If you're ever asked to explain why buffer works, so anything like that, explain why buffer works, the first thing you do is you give the definition. So remember your definition because you'll need it for a mark. Second thing is you give your equation for the buffer. Now the buffer equation is always just the dissociation of the weak acid. So here's your weak acid, is dissociated into its conjugate base in H+. So you won't necessarily get ethanoic acid, although it's really common. You might get any one, but all you do is take 1 proton off, and that's it. And that's your equation. And that'll be 2 marks straight away. Okay, some of the easiest 2 marks you'll ever get. Anyway, so let's move on. In the buffer, you're going to have that ion. You can see the ions here, and you have all those. But you're also going to have Na plus as well. Remember, the Na plus doesn't change. So if you use up some of your conjugate base and your acid, the sodium doesn't change its concentration. So the sodium can often be the one in the highest concentration in the buffer because it's not doing anything. It's just floating around. Okay. Now, let's have a look at it and see how it actually works. And I love this little graphic. I think this graphic works so well with groups, so I'm hoping it's going to work with all of you. So let's imagine we have an amount of weak acid and we have an amount of conjugate base. So just say we add exactly the same amount. And then that will produce a small amount of H+. Now, just a small amount, because this is partially dissociated. It's a weak acid, so it's partially dissociated. So it produces a little bit of H+. We've made it bigger just to make it obvious. It's much less, but yeah, but that makes sense. Now, you've got a little bit of H+, okay, and then you add acid to it. So you add acid, you want to maintain the pH. This is a buffer. It's about minimizing the pH change, small amounts of acid and pH or base. So I've added a little bit of acid, HCl. That means I'm adding H+, because it's a strong acid and it's made of H+ ions and it's fully dissociated. So it goes into the buffer, which means this is going to come up. Okay, well then if that comes up, the pH changes. So the pH will change. Okay, so what does the system do to minimize that pH change? It's all about Le Chatelier's principle. So if the H+ has come up, that means you've got an increased concentration of H+, which means if you increase the concentration of H+, then Le Chatelier's principle says it will try and minimize that change and put the equilibrium to the left. To put the equilibrium to the left, we need to do a reaction, and the reaction is going to be H+ plus CH3COO- to make that. So that means if I do that, I will remove the H pluses, and you see it removes, but also remove some of my conjugate base. Okay, now as well, if I'm doing that, I'll make some more acid. Okay, so let me just put that back, just so you can see it again. So look at this, and look at that. Okay, and there you go. Okay, that means the H+ has gone roughly back to where it was at the start, which means the pH is staying the same, because you work out your pH is pH equals minus log of H+ concentration, so the concentration of H+ controls your pH. And that's how we do it. Now, that means equilibrium shifts to the left to minimize the change in H+. Now, how do you answer that in terms of a question? Okay, so in terms of a question, you add H+ to the solution, and they'll combine with the ethanoate ions until the ethanoate ions are all used up. And then the pH completely changes, okay, once the ethanoate ions are all used up. H+ will remain similar, and so will the pH. Similar, not exactly the same, because it minimizes the pH change. Now, how do you get marks? You get marks by, first of all, doing this equation. So you're showing that equilibrium goes to the left by this being added to this, which makes that, okay? And so that will get you a mark if you're asking to explain how a buffer works. Okay? Now, we'll go through both of those at the end, but this is the next one. A buffer is made with weak acid and its conjugate base, and this time we're going to add an alkali, sodium hydroxide. Now, the sodium hydroxide does a special little reaction. The OH- reacts with the H+, therefore lowering the amount. So you can see it here, and it works through this neutralization equation here. So if that is the case, we need to bring that back up again. So because you've removed the H+, the equilibrium is going to want to go to the right to produce the H+ and bring it back up again. So it goes to the right. Okay. Now if that is the case, you'll get more conjugate base, you get more H+. Okay. And the H+ is back at its original level. But you get marks for putting the neutralization, for putting the fact that the OH- is reacting with the H+ to take it out. So that's your mark there. We're going to go through some questions on this to make sure you know how to answer the questions anyway. But that's how both of them work. So equilibrium shifts to the right to minimize the change in H+. So we know if we add the OH to this solution, they'll bond with the H+ ions, and that's your mark there, OH- plus H+. Okay, this lowers the H+, equilibrium shifts to the right until this weak acid runs out. Okay, and when that weak acid runs out, then your pH will change. Your buffer will not work. Okay? Now, let's go through different versions. There's two versions I'm going to go over of how to explain how a buffer works, because this is what we've been talking about all the way through. So the first one is carbonic acid. Now, we're going to talk about a further question later on about carbonic acid that basically says with carbonic acid, what is the ratio between the acid and the carbonate ions, or hydrogen carbonate ions. But for now, we're just going to use it to explain how a buffer works. Now, this is the buffer that happens in your blood. So it keeps your blood at roughly 7.2 to 7.4 pH. So, explain in terms of equilibrium how the carbonic acid hydrogen carbonate mixture acts as a buffer in the control of pH. Okay, so we've got to explain it. And this could be a 4 to 6 mark question. So first thing, you do the definition. So the definition would be a buffer is a solution that minimises the change in pH upon addition of acid or alkali. That would get your first mark. Then you have to talk about the equilibrium shifts, and you have to use the equilibrium equation. So the equilibrium equation is based on the carbonic acid, and there you go, H plus HCO3, and there we go. Okay, now remember that's 1 mark, your definition is 1 mark. Addition of H plus causes the equilibrium to shift to the left. So we want to get rid of the H plus, so it shifts to the left, that's your mark. Addition of OH minus shifts to the right because you're removing the H plus, so it shifts to the right. Okay, the action of buffer is 2 equations. So if the acid gets added, then you lose the H plus by adding it to the hydrogen carbonate. If the OH gets added, then you do this equation. And that is all your marks for a 6 mark question. Okay, remember your definition is your first mark, your equation is your second mark, the shifts are the next mark, and the equations are the next mark. Can be anywhere from 4 to 6. Can't exactly say how many marks it's going to be, but it used to be 6, tends to be a little bit lower now. And that's how you do that. Okay, so let's go to the next one. So we have got partial neutralization now. So we have got 2 ways of making a buffer. One way is when you add the conjugate base to the weak acid, and our second way is where we had excess weak acid and a strong base. So how does that work? So that works with excess weak acid. That means basically it will be partially neutralized. So let's get this out of the way here. So that'll be partially neutralized. So if I add my acid here of 1 mole per decimeter cubed, add the sodium hydroxide to it, that will use up half of that. Okay, so if that is the case, that's in excess, that's all used up. Okay, now if that is the case, that means I'm left with 0.5 of this and 0.5 of that. Let me just go back again, just say that again. Okay, so remember, this is 1, this is 0.5, it's a 1-to-1 ratio. So half of this will be used up and half of it will remain. We know that the sodium methanoate is fully ionized, and we know that we're going to get our conjugate base as a result because that's our product. Okay, and also on top of that, we're making water. Water doesn't make any difference to anything because it's all aqueous anyway. So as long as we have too much acid, we use up all the sodium hydroxide, we can make a buffer. Really, really, really easy to make. So, how does a buffer work? A chemist makes up a buffer solution by the following method, and you can also there's 2 different ways of doing this. You can write down what the pH is if you're ahead of the game, because I've given you all the details, or you can just explain how the buffer forms. So let's put this to the side. So how does the buffer form? First of all, the acid is in excess. So you could work that out by doing 0.05 times 0.075, okay, 0.05 times 0.250, and you'll find that the acid is in excess. Now, you have the equation of HiO3 plus the sodium hydroxide goes to NaIO3, and that basically means there's your conjugate base. So you need to include the equation. If you're talking about how this works, you need to include the equation. You also have to mention this partial neutralization of the HiO3, and this forms your conjugate base, IO3 minus or NaIO3. The buffer contains HiO3 and IO3. So basically you're telling the person who's marking it that you've got your weak acid and you've got your conjugate base. Okay, so that is how this buffer works. Now if I'm going to do this method as well, I would probably put my definition for a buffer in. Remember, your definition for a buffer is a solution that upon addition of acid and alkali minimises the change in pH, or the pH change is minimised upon addition of acid or alkali. But if I'm asked to say what this type of one does, how this makes a buffer, you want to say what's in excess, what's the equation for the partial neutralisation, okay, and do the buffer containing the HA and the A minus, okay, and it might even be helpful to just give the actual equation for the acids. So basically just going, this basically is, let's get rid of that. Okay, excuse me. Okay, HI3 goes to H plus IO3 minus. So we've got our mark for this. We've got a mark for determining which one is in excess. We've got a mark for saying what the partial neutralization is. Okay, and then we've got a mark for a bit of explanation down here as well. Okay, and that is how you explain how a buffer works when a strong base is added to a weak acid. Okay, and that is the end of how you make buffers. On the next video, we'll talk about the calculations to do with buffers, which can be quite complex. And I'm going to go through every single type of calculation that you'll need. Enjoy.